Hi, can you able to hear me? Hello.
Yes, I can.
Yes. You can present your slide using there is an option present now in the right side.
I was trying to look for that option. I'm
Yes.
not able to find that.
You are using in the laptop, right?
Yes.
There will be an option right in the right side. There will be option present now. Can you able to find?
No.
In the down there are a few buttons like turn on captions.
Mm-hmm.
Can you
It will be in the right down corner.
Let me see. Does the browser? So I'm using Google Chrome right now. So
yes,
it should
yes.
work, right?
We are also using in Google Chrome only. There is a in the right left corner there will be a sorry in the right bottom corner there will be a present now button.
No, after you went offline, as I was trying to look for that, and I was going to ask you about that.
Sir, or you might see there might be three dots.
Yes, yes.
Yeah, you click the dots, or maybe in the
In,
three dots, there might be some options, presentation or present now something.
so here it has just change layout, full screen, turn on captions, settings, and use a phone for audio. There is no present now option.
Maybe I think they may not be used in you have logged in with which mail?
This is Gmail.
You were logged in with Gmail, right?
Yes.
Then
Oh no, this could be my university email.
yes, that might be they have blocked that option.
Oh, so if
Because
should I just
last time everyone has used the same and they can able to do that.
okay, so let me just go out and
Yes, you can
log in.
join
Okay.
with your Gmail and we can try with
Okay.
that. I will pass that. sir, I will introduce you, and we will start the session. Kindly, everyone, please keep your audio in the mute, and we would like to invite Dr. Rachit Bhatia, an aerospace engineer working in Space Nova, Colorado, US. He has done his PhD from Utah State University, same from US, and he has specialized in space navigation, linear covariance analysis, spacecraft guidance, and controls. He is right now working on designing, developing, and testing various mathematically intensive software applications. Projects His projects also include developing and conducting research related to space situational awareness. So I would like to invite Dr. Rachit Bhatia to give a lecture on spacecraft guidance and navigation to our students. So he is right now he is at night, near about midnight in US. It is around 11:30 p.m. He is spending his time with us right now, and this is a great, sir, great work. We didn't expect this, and you are giving your great thing for this for our students especially. So I would like to request you to start the session, and if students, anyone having queries, you can type in the chat section, so that at the end we can request to clarify those doubts. Okay, sir, you can start now.
Thank you, Dr. Krishan. Welcome, everyone. I will go over the presentation overview. So, as Dr. Kishan introduced me, I am Rachit Bhatia. I'm working here. I finished my PhD in aerospace engineering in December 2019, and I started working in March as an aerospace engineer in Boulder, Colorado. So I'll go over my background and then some past projects. And the idea for today's presentation is entirely to introduce how to approach a problem, and also to help you understand some of the mathematical tools that I used for my PhD project. From today's presentation, I want you to at least get introduction to these three tools or three important concepts that are very common in estimation problems and controls problem. And then after introducing you to those concepts, I will also go over my PhD project and the work that I did for my PhD. So hopefully it will be useful. And regarding my background, as Dr. Kishan introduced me, I finished my bachelor's in India from SRM University, and then since 2015, I've been in United States. I have been working towards my master's and PhD. I finished in December 2019, and now I started working as an aerospace engineer over here. My experience during
Sir, actually,
bachelor's,
1 minute, sir. Actually, like from your side, your end, there is a small noise. I think there is a problem with the microphone.
Is it better now?
Yeah, now it is okay. Yes.
Okay, I'll just hold this. Okay. So for my experience, I started working in May of 2013 when I did my internship during my bachelor's at Indian Institute of Astrophysics, Bengaluru. And then over here, I worked as a graduate research assistant while doing my PhD, and I also worked as a graduate teaching assistant for one of the semesters over here. I was also a member of an undergraduate student team up at Utah State University, where we worked on CubeSat, which was to be launched. Actually, it is still to be launched by NASA under CubeSat program. I was also a team member of Utah State University rocket team, And now I'm working as an aerospace engineer in Boulder, Colorado at SpaceNav. Some of the past projects that I've worked regarding the state estimation projects, I will present today the first one, and this is the project that I worked for my PhD, the revolution in autonomous orbital navigation. I will go over the details in a while. The second project I did for one of the coursework that I did at Utah State University. It was also a very interesting project where the problem was to estimate the relative state between a UAV and the aircraft carrier and check the feasibility for an automatic carrier landing problem on an aircraft carrier. Another project that I did was an initial orbit determination of these resident space objects, RSOs, we call, are basically an orbital debris somewhere in geo orbit. And so the idea was, if we have an optical observatory stationed at L1 halo orbit, Earth Moon L1 halo orbit, then can we detect these RSOs in geo altitude and do some initial orbit determination of those geo RSOs. I also worked on some of the controls project. The previous project that I was talking about, Earth Moon L1 halo orbit observatory, extended it into a controls project where now we have an observatory. Then what kind of station keeping will be required for such an observatory up there? So I developed LQR controller and analyzed the thrust required for station keeping. I also worked on a spacecraft air determination control system of a CubeSat, and I designed a feed-forward linearized inner and outer loop controller to control the attitude, basically the orientation of a spacecraft. And as I was telling you, I was a member of a rocket team at Utah State University. So I helped this to represent the problem, to set up the problem, and then go on to solve it. If you have a linear system and you have n cross 1 or some n-dimensional state vector, similarly a k-dimensional input vector and m-dimensional output vector, then the dynamics of the system can be written in terms of state and input as follow. And here these A, B, C, and D are the matrices which define the system. And this is very convenient form because this is a linear system, and it is easily solvable, the differential equation. And it is a very powerful system because all the state transformation and everything can be done very easily. So as I was telling you, if you have a given initial condition, then you can solve that previous differential equation that I showed you, x dot equals ax plus bu, and you can get this solution. And here the first term is 0 input response, and then the second term is 0 state response. And in the time invariant case, you can write, so this is the state transition matrix. So this is the state at time t, and then we get the state transition matrix, and this is the initial state, and then this is the other term. So say if input is 0, then we only need state transition matrix. And in many cases, as in my problem, it is mostly time invariant for a simple problem or simple dynamics, specifically orbital dynamics. Then it becomes really easy to to model the system and solve the problem. So if the system is time invariant, then you can also write the state transition matrix in this form, where A is that matrix that I showed you in the previous on the previous slide of the differential equation, x dot equals ax plus bu. So we can get the state transition matrix. Now, the way you can understand this is that state transition matrix is basically a matrix that helps you transform a state from state transition matrix to transit the state from one time to the another time. So here the state transition matrix is helping us to transit the state vector from t0 to t given time. So it is a very important thing. Now, the reason I showed this to you was that now when I will set up the problem and I'll introduce you to the next tool, which is observability analysis, then this will be used. So you will see how convenient it is and how handy it comes when applying such mathematical tools. So now, what is the problem that I will be discussing with you? I've already told you the title, the revolution in autonomous orbital navigation. Not a very good title. But you might already know it is something about autonomous orbital navigation. Over here on the slide, you can see this statement from the decadal survey. So here in United States, and the National Research Council presents this decadal survey of the most important things that they need to solve for the next technological advancement. And over here, they present this goal where they say any planetary spacecraft, regardless of its specific destination, must cope with the fundamental challenges of traveling long distances from Earth and the Sun, surviving and operating over the resulting long mission duration, and operating without real-time control from Earth and with limited data streams. So what they're trying to convey is this problem which we will face and which we currently face is for a mission, for a deep space mission, we are entirely dependent on communicating with ground station, which is Deep Space Network at NASA, or the ground stations of ISRO, where to control and navigate the spacecraft. So can we solve this problem where we do not need ground contact with Earth and we can autonomously navigate? And this will not only help us increase the reliability of the system. Say if you have sent a mission to Moon, then you cannot contact with the mission when it is on the backside of the Moon. It is not able to contact the Earth unless and until there is a relay system. So you need such a system, especially if there are if it is a manned mission, if there's a crew on board, so as to make sure that everyone stays safe in case something happens. So this is a very critical problem, and if you get to solve this, then it will also give more bandwidth and data stream. It will clear the data stream for communicating science data instead of communicating with the ground for controlling and navigation. So it will increase the productivity, it will increase the output of the mission, at the same time maintaining the safety of the mission. So as I've already told you, the motivation for autonomous orbital navigation is to improve spacecraft's autonomy and versatility, reduce complexity and cost, enhance spaceflight safety, judicious use of onboard resources, and increase adaptability for varying space environment. Now, the last point, the reason I give that is there are many different options for autonomous orbital navigation, many different concepts that have come up, like X-ray pulsar, using X-ray pulsar for navigating, or developing a GPS type network throughout the solar system to navigate. But each of these concepts have certain limitations in certain space environment, and the concept that I will present today is using gravity. So it seems to be much more universal than these other concepts, and much more adaptable to these varying space environment rather than being limited. So what is the solution idea? The idea is that there have been these missions which used very powerful accelerometers on board to map the gravitational field of Earth. And how did they do that? Is using these powerful accelerometers and also the GPS data. So these missions were in low Earth orbit, so they were getting they were generating these measurements on board. They were also getting GPS data, so they knew where the spacecraft is already, and they were using these accelerometer measurements. And using that, what they did was they measured how the gravity changes from with respect to position. This term is called gravity gradient. And when you measure gravity gradient, then you can generate this gravitational map. Now, can we reverse this problem where if we still have this very powerful accelerometer on board and we have the gravity map, so we do not need GPS data or navigation or tracking data anymore, but we can use these two measurements to autonomously navigate in space. So that is the entire idea. And the reason I presented this way is I'm trying to convey how to approach the problem and how to set up the problem, which may be helpful when you are doing other projects later on for your bachelor's or master's or other academic requirement. Now, I also want to present the power of mathematical model. So whenever there's a system or problem of interest, we try to set it up mathematically. And often there are two major models that are set up. One is dynamical model, which encapsulates the forces causing the motion of the system, or causing the motion of the system. So all types of forces. If you have a spacecraft, there will be gravity, atmospheric drag, solar radiation pressure, lunar gravity, etc. And then there's the measurement model, which defines the measurement information that is being processed to estimate the quantities of interest. Now, in this case, quantities of interest would be: what is the position of the spacecraft? What is the velocity of the spacecraft? What is the orientation of the spacecraft? So if we can set up these two models perfectly, or very with high fidelity, then we will be able to estimate the quantities of interest. And that is what I do. So I set up a problem state vector. Now the states here are, the state vector is the very first one, X, and then it has three major sub components. Or I've done the segmentation so that it is easier to read. One is spacecraft states, which include position, velocity, quaternion, which is the orientation, angular velocity, and the position of the center of mass of the spacecraft. Now I want to estimate these states. I also want to estimate the environmental parameter states, which include ballistic coefficient, reference atmospheric density, and scale height, which define my drag model, atmospheric drag model. because it was very important to know what kind of atmospheric drag is acting on the spacecraft. And finally, I would also like to estimate the accelerometer state, which is the position of the accelerometer with respect to the origin O of the spacecraft, and then bias, and then scale factor, and misalignment. So these are some of the accelerometer, or mostly for any sensor in inertial measurement unit. These characteristics are very important if you want to model the measurement, if you want to represent the measurement model of the sensor. So I want to estimate all these quantities. Now, how will I approach? Again, now I will first define the dynamical model and measurement model mathematically. I write the state dynamics x dot as a nonlinear function of state and time, and I add this process noise, which is W, which is basically we add this so as to include the noise which cannot be modeled. So the dynamics here, remember, this is what we are trying to do here is we are trying to tell the system what kind of real world forces will be acting on it, and we are trying to model them mathematically. And when we do that, there's always some force that we cannot model, or we some anomalies, and that, for that we use process noise over here. We add this to the state dynamics so that our system remains very much reliable and easier to work with. And then the second model is measurement model. Over here, I have the accelerometer measurement, and then these are the function of the state vector. And then I add measurement noise. For all the measurements for any sensor, there will be some measurement noise acting on the sensor. Now remember, an accelerometer cannot measure gravity. So if you have an accelerometer on your phone, if you put it on a table and leave it still, it will not measure gravity. It will measure zero because it measures the reactive force. So we are not trying to measure gravity by an accelerometer. What we are instead doing is we have these two accelerometers, or even if we have just one, we offset it from the center of mass, and since it is rigidly attached to the system, there's this tension force acting on the accelerometer. And when this accelerometer measures that tension force is a function of the gravity. What is the gravity gradient? What is the difference between the gravity with respect to this difference between the center of mass and the accelerometer position? And that is what we are measuring. So we are not using accelerometer to measure gravity here. We're using accelerometer to measure gravity gradient. So that is a very big difference. And once we have set up this dynamics and measurement model, then we do linear modeling. But before that, I would like to introduce, just go over the procedure. So we have already set up the nonlinear model. So what now I need to do is linearize those equations, because as I told you, it is always important to linearize these nonlinear models, because it's so much easier to solve linear differential equations and to work with linear models because of their property. So when we linearize them about the reference state vector or the nominal trajectory, which in this case I define one of the LEO orbit. I'll discuss, provide the details in the results section. Then we also derive linearized equation of motions and measurement partials. You might not be knowing about these two terms. I'll discuss them in the next slide, so it's okay. Then next, I conduct observability analysis to check the feasibility of this concept. And then I conduct linear covariance analysis. I need to discuss that as well in the following slides, and then I simulate and conduct error budget analysis. Now, the reason I have given you this procedure over here is to tell you that we are here right now, nonlinear models. We will first linearize it. I'll talk about that. I'll also talk in the same slide about the Jacobians and the measurement partials. And then those will be used in observability analysis, linear covariance analysis, and finally to know the error budget analysis. Now, the reason I want this error budget analysis is what I'm trying to do here is I've set up the problem. What do I need to do is first, using observability analysis, I will check if the given concept can work. Basically, what I will check, I have these measurements from very powerful accelerometer. I want to estimate position and velocity and orientation of the spacecraft. Can I measure those quantities with the measurement that I'm thinking, or do I need more measurements or different types of measurement? Do I still need GPS? So that question will be answered over here when I will conduct observability analysis. Then if I can do this, if it is feasible, then the other question that I want to answer is, okay, I can do this, but I need an accelerometer with a noise level which is not possible, or I need 8 accelerometers, 10 accelerometers. So I, using linear covariance analysis, I will do that, or error budget analysis, I will do that. I'll answer that question, where I'll see if I have 3 accelerometers, what is the error? What is the final error in the position? If I have 6 accelerometer, what is the final error? And also I'll check what part of the what parameter is contributing to that error. So we'll talk about that, all of that, but that is the overview of the problem that we are solving. Okay, linearized model. So we linearize the model over here. So this is the Jacobian. This is the equation of motion Jacobian over here, where we take the partial with respect to this nonlinear function with respect to the state. And similarly, we linearize the measurement, and we take the partial with respect to the state vector. Now, x bar is the nominal trajectory. So we evaluate it for a nominal state vector. And hence, we get the Jacobian and measurement partial. And we use this in the observability analysis. Now, what is observability analysis? I've already introduced you to the state space representation. Now, what the observability analysis say is that the state space equation is said to be observable if for any unknown initial state there exists a finite t1 greater than 0, such that the knowledge of the input u and output y over that interval is sufficient to determine uniquely the initial state. Otherwise, the equation is said to be unobservable. Now, this is a very complex statement. So the only reason I read this was to now help you understand this. In a gist, what this statement is saying is that the system is observable if for a unique output, you get a unique input or unique initial state. So what that basically means, if you have some measurement, then can you know what state vector caused that measurement? And if you can, then you can know your state vector. And so if the system is observable, then we'll get to know that the measurements that we are taking or the information that we are processing is sufficient to estimate the state vector or the states that we are trying to estimate. And that is very powerful, because without even making the entire simulation or doing any further analysis. Just by doing observability analysis, I can get to know if this problem will work or not. So how do you do that? You use state transition matrix. You still need to formulate that state transition matrix, do some partials, get the measurement partial h, and then use those to compute observability Gramian for all the m measurements. And when you do that, if the observability Gramian is full rank, and this again is linearized time variant discrete time model. There are different forms for this problem. The problem is can be categorized as a linearized time variant model. So we are using this form. And if this observability Gramian, and when I say Gramian, it is basically a matrix. It is just a mathematical name term for this matrix, observability Gramian. If it is full rank, if this matrix is full rank, then you know that your system is observable and you can estimate all the states from the given measurement. Now I present you the result. So what I did over here is I have a 3-axis accelerometer. And if it is the spacecraft is in a circular orbit, then I get full rank. If it is in elliptical orbit, then I get a full rank. And this point mass, 4x4, 8x8 are different gravity models. So the gravity model that I fed into the system is either the gravity is uniform, which is point mass. Then 4x4 is a little bit not uniform, and then 8x8 has a much better resolution. So when I did this for this orbit, 7,000 kilometer LEO and 56 degree, this is the eccentricity, and I get that I can estimate the position and velocity of the system of the spacecraft for any of these conditions, which is very powerful. Now, if I repeat this for the attitude or the orientation as well. So now I not only want to estimate the position, velocity, I also want to estimate the orientation. Then I realized that, okay, for point mass and circular orbit, I cannot observe because the rank is 8 instead of 9. 9 here means 3 components of position, 3 components of velocity, and 3 components of attitude, orientation. So we cannot observe all the states when it is in this configuration, which is good to know, because first of all, it will never be point mass, and then we can configure our system based on this result. We also see the condition number, which is an important characteristic when you find the rank, and see how it decreases. So the lower the condition number, the better the rank, and better the matrix is much more stable, numerically stable. So we can see how for a much higher gravity model we get better solution, and that is what we expected. So this confirms our insight about the system, that the concept can work, and we can use accelerometer measurements to at least measure position and velocity. Regarding attitude, we realized that it is weakly observable, so we decided to add a star camera, which gives you the orientation of the spacecraft, another sensor. And then we also, as we noted, that orbital dynamics and higher order gravity model improves the observability. Next, I go on to define linear covariance analysis. Um, we so when for any estimation problem, we basically divide the system into two models: truth model and filter model. Truth model is set up to mathematically represent the real dynamics to the best of our knowledge. What will the spacecraft experience or the system experience in the real world? And it includes complete environment model and all the states necessary to define the system dynamics. Whereas the filter model is what the flight computer, which will be working to estimate the system, these states will experience what based on the measurements it is getting from the sensor and everything. So flight computer is always has a low fidelity dynamics model because there is constraint on computational resources and storage resources. So uh, filter model is used to define that part of the concept, and it includes only the states of interest. By having these two different models, we can we can what we say propagate and update these two different models over the time period to see how they emerge, and then we can check the error at different epoch, or say the final time of the problem. And we can see, obviously truth will perform better, but what is the comparison between the filter and truth? And then we can see the navigation error. So that is what I will discuss next. And here you might see some equations. You should not be afraid. These the equations that what they are conveying here is that you have a filter covariance, you have a state transition matrix, you have a noise covariance matrix. So this equation is called Riccati equation. And what it does is it is propagating the covariance over time. So what is covariance? Covariance is what is the uncertainty in the state. If you are defining the position, how sure are you that your position is 1 kilometer and not 1,000 kilometers? So we put some uncertainty in there, saying that okay, my position is 100 meter, but then it could be plus minus 200 meter or plus minus 500 meters. So that is what covariance is used for. So this equation propagate the covariance over time. It and when I say propagate, it moves the covariance as it emerges over time until throughout the orbital period. Next, we update the covariance. So we are not only uh, propagating. Propagation is basically uh, uh, based upon the dynamics that are working on the system. The update is also needed because we are getting some measurement about we are getting some information about the system and the dynamics, and we can use that to better our uncertainty. For example, if I start at position with a position uncertainty of 200 meters, and next uh, uh, in next 10 seconds I get a measurement, say GPS measurement, and as you know, GPS measurement is accurate up to 10 meters, then my uncertainty decreases from 200 meters to tens of meters. So that is how we update the filter covariance. So this equation updates the filter covariance. This is the Joseph form, and then this is the Kalman gain. And we use these, and similarly we also define an augmented covariance. Now, so for linear covariance analysis, what we are doing is we are defining two systems: filter covariance and augmented. Now filter is itself, as I've already defined, and augmented includes both truth and filter. And when it propagates and updates it throughout the time period over here, orbital period, as many orbits that we are running, I think I'm running 5 orbits for my simulation, then we will see how the system is behaving over this time period based on the given measurements and the dynamics that we have defined. And based on that, for the given scenario, say we had measurements for only 3 accelerometers, then we will see that the final position error is some hundreds of meters. But now if we rerun the system with 6 accelerometers, then we will see that the final error decreases to 50s or 70s of meters. So then we can conclude, okay, yes, if we have more accelerometers, we get better solution. So that is the um, entire purpose of doing this thing. We did observability analysis to get some understanding if the concept will work, and now we are doing linear covariance analysis to know the system is working, but at what cost? What are the specifications needed to make the system work or to get the better answer? So that is what the idea is here. You can also do Monte Carlo analysis for this. However, Monte Carlo becomes very complicated in terms of it takes more computational resources, and you have to run it for hundreds or thousands of runs. But linear covariance analysis is an easier way to get the representation of the same solution. And the only caveat here is that you have to linearize the problem first and then solve it. But for orbital problems, orbital dynamics problems, the problems usually are very linear and very easy to work with. So you can easily use linear covariance analysis. As I've already defined, the performance metric over here is the navigation solution at the final time. What is the position? What is the velocity error at the end of the 5 orbits? True navigation error is defined as the difference between the true and the filter uncertainty. And we use that to know how the system is performing. And this is done in local vertical, local horizontal frame. It is just a different frame of reference, easier to understand and visualize. So that is why we use it. We also had, if you remember, environmental parameters and accelerometer states. So we get the true navigation error on those as well. And finally, we get the navigation error budgets and sensitivities. I still need to talk about navigation error budgets and sensitivities. So here we go. What do I mean about this navigation error and sensitivities? I define the different error groups which can affect my system. One is initial uncertainty. When I start the system, how sure I am about the position and velocity, about the orientation and angular velocity of the spacecraft. What is my best estimate or my initial uncertainty about the center of mass position of the spacecraft? What is the translational process noise? What is the rotational process noise? What is the uncertainty on the atmospheric model parameters, accelerometer parameters? So these are different error groups that I've listed. And what I do then is run the lin curve for each of these error groups. Doing that, when I say each of these error groups, what I do is first I run it for all the error groups switched on. So I have some initial uncertainty for spacecraft position, velocity, orientation, angular velocity, etc. So I've switched all these error groups and I run the simulation. I get some final error. Then I rerun the simulation where I switch off all the other error groups but one, say very first one. And when I do that, then I repeat this for all the error groups, and I can get the contribution of each of these error groups towards the total. And I'll show you that in the results. But before that, we will set up the simulation. So I have this spacecraft, which is spherical in shape and with following characteristics. Then I have the drag model parameters. I'm using a very uh, simplified drag model over here. Then I also define the time constants on these different atmospheric parameter states and accelerometer states. And I have not discussed that with you, but these states are modeled as first order Markov process, which is basically just the dynamics, how these states will behave over time. And then I also define the initial uncertainty that I was talking to you about. What is my initial uncertainty on spacecraft position? So here I have initial uncertainty of 500 meters in radial direction and 1000 meter in along track and cross track. Then my initial uncertainty in velocity is 1 meter per second, and similarly the other values have been listed. I divide the problem into three parts. So I have I solve this problem for different systems, where because I have all these parameters and they can be multiple combinations. So what I do is I have one high cost model which has everything uh, very high fidelity and everything very nice, based because we have a high cost system. We have all the best possible model and equipment to get to estimate these, very nicely get the initial estimate of these parameters. And hence that you will see that translational process noise is lower on this, and then aerodynamic process noise and rotational process noise are lower on this. So this is just a way that I'm setting up my problem, because instead of running it with all these parameters changing, I set up three cost models. One is high cost, moderate cost, and low cost. And high cost is the best model. I have everything great. So this should theoretically give me better results. Then moderate will give me not so good results, and low cost should give me okay results. That is the idea over here. Similarly, for sensors, I have high cost, moderate cost, low cost. When I have high cost, it has a very nice, very low measurement noise. I know the position very well. I have very low scale factor and bias uncertainty, etc., etc. While for moderate cost, it is not so good, and for low cost, it is okay. So that is the idea how I have set up the problem. Okay. Now I define the orbit. What orbit I'm using? I'm using this LEO orbit, 7,000 kilometer eccentricity, 50-degree inclination, etc., etc. So all these parameters. The reason I show these parameters is because now when I will present the result, when you visualize those results, you can see how these things changes. Also, another parameter over this in this problem is rotating or non-rotating spacecraft. So we can have a spacecraft which is rotating, and then we can also have a spacecraft which is being controlled by thrusters and such that it doesn't rotate, so that the system stays much more stable and the performance is maybe better or worse. We will see so we want to see how much rotation affects. And one of the reason is that we are proposing it for navigation purpose. Can we still navigate if the spacecraft is doing some maneuver, if it is using its thruster? So that is the idea, to see if certain disturbance in the environment will improve or worsen the result. So now here I present the first result, and this is for low Earth orbit, 50-degree inclination, high cost. I only present high cost results for today's presentation, just to keep it short. So I have non-rotating inertially fixed spacecraft, 3 accelerometers, 1 star camera. Baseline is basically what is the distance between two accelerometers. So I have 0.5 meter baseline, and then large time constant. So all the you don't need to worry about because I've not talked about it. But basically this is the setup, and you can see the contribution. So we started somewhere around, for radial, I think for a long track it was 1000 meter, and with the measurement it comes down to very nice, hundreds of meters. This is the total error. The maximum contribution is towards from accelerometer position. So if we can improve our estimate for accelerometer position, then we will improve the total error as well. So that is the idea. That is what we are getting in the long track. Similarly, the cross track. What are the major contributors? And radial. Now we see that a long track and cross track are the major contributor, because look, they come down from to 50s or hundreds of meters, whereas radial is already down very much. So, and then I have magnitude. So having known that, from now on I will only present the magnitude results. I present another result for orientation. So the above one was position. Now for orientation, similarly, we can see what are the different contribution from what. So here for orientation, the maximum contribution is from star camera noise. So if I can get a better star camera, then I will get better results. So that is what we are getting from this, to know from this result. Similarly, what is the second contribution that is rotational process. If I can make my model such that the rotational process noise is lower, then I'll get better results. So that is the whole purpose of doing this analysis. I tabulate those results for the final time error, and here we can see that from thousands of meters of initial uncertainty, we finally, at the final time of after 5 orbits, we get some hundreds of meters of in spacecraft position, and very low error in spacecraft attitude as well. And we also see the error sources, which are the major contributors. So these are the top. Error source 1 is the top contribution from, and then error source 2 is lower, and then error source 3 is much lower. So that is the idea of presenting these results. I repeat these results for, as I said, non-rotating and rotating. So we see that for rotating, it is improving. So that was another interesting result, that rotating improves. So this is rotating nadir pointing, but it is improving. So that was interesting, and how the error sources are also changing. Instead of accelerometer position, now the accelerometer error is the top contribution. Similarly, if I have more accelerometers, instead of 3, I have 6, then the results improve, which was expected. So again, and now the error source 1 is only star camera noise. So all we need to do is have 6 accelerometers and get a better star camera, and we will be good. So GPS gives us tens of meters. We're already getting 73 meters, which is not bad in low Earth orbit. Similarly, now if I improve the baseline, instead of 0.5 meter, if I have it for 1 meter, then the results are comparable to having 6 accelerometers. So instead of having more accelerometers, I can just have a bigger spacecraft. So that is another interesting result. And similarly, if I have more accelerometers and also a wider baseline, then the results are the best. So that is the, so I proved that the concept works. Then I proved, then I showed what are the major contribution sources towards the error, and how that error changes for different scenarios. And that is how I think I want to show how to approach the project, and how maybe you can do work on your problem, where you have different parameters and you can divide it into different cost models, and then you can use these mathematical tools to work through. In the end, I will present the summary for the result. We have seen that only high cost system is performing great. When I do for moderate cost and low cost, this is the performance is not so good. For moderate cost, it is 15 times position error is 15 times. For non-rotating, and 47 times the rotating compared for that of high cost. And similarly, we have also seen that the best result is from 6 accelerometers with 1 meter baseline, which was expected. So I'll conclude here. I'll present the conclusion of the work. We have seen that we need ultra precision accelerometers to actually make this possible. We I've not presented here when I uh, redo these results for polar orbit, the results are better than that for a 50-degree inclination. Uh, so just changing the inclination also improves the result. The accelerometer error is the major source of error for many of the scenarios we have seen, and other relevant error sources were accelerometer position uncertainty and star camera measurement noise. What was the unique contribution of this research? So we introduced this concept. We did observability analysis to show that this concept is feasible. Then we conducted linear covariance analysis to show what kind of specifications are needed. And with error budget analysis, we showed what are the major contribution, what sources are contributing towards this error, and how can we improve that. For future work, we can include more uncertainties, have more orbital regime, have more extensive testing of simulation. So those are some of the future work. And this is the publications that I've worked on for the similar. I've published for this concept, and these are my references. With that, I will conclude, and I think I've already taken more time. But thank you for your attention, and I hope this was helpful, informational, and yeah, I'll be happy to answer any of your questions. So I use MATLAB. Yes, I used MATLAB for our entire project, but excuse me. But you can use other softwares as well. That is not a limitation. I felt MATLAB was the most convenient one, but nowadays Python and other softwares are also coming up, which are much more easily accessible. So, yeah. Yes, and physics and mathematics is very important to understand the dynamics. I've deliberately not included those in the presentation. Otherwise, the presentation would have been much longer. But yeah, read the literature. Try to understand the physics. Keep your concepts clear about. So this is an orbital dynamics problem. So in space environments, you should know what. The basics of orbital dynamics, and how does these sensors work. That is what I will advise. Yeah. uh, so tell me again your question. Uh, US, US, I think it is very difficult as an aerospace engineer to crack, because over here, anywhere outside India, or even for any country, the problem that comes with aerospace engineer and specifically guidance, navigation, and controls is that these technologies are ITAR restricted, which is an international treaty, and if you are not a citizen of that country, you cannot work. Um, the position that I'm working on right now uh, uh, is also ITAR restricted, and the the reason that I was able to get this job uh, was that my work is more into simulation, and the kind of the position description uh, was that I do not need any access to the ITAR restricted uh, uh, material or resources. So it is a very tricky thing. It is if you think you can come to US and work for SpaceX, that is not possible. There are very limited job options if you are not a citizen. So you need to plan for that. However, in India, there are already many startups coming up in aerospace, and you need to and they are working on some similar problems, orbital dynamics problems. So I would say keep an eye on them, and I'm not saying all the positions are ITAR restricted, but 98% are. So plan accordingly. No, let me. No, so what kind of signal? What do you mean by signal? And so yeah, so when you are, so there are different types of maneuvers. First of all, you can do plane changing maneuver. You can do altitude raising maneuver. You can do altitude decreasing maneuver. You can do Hohmann transfer, as you might have read in orbital dynamics. If you are if you're targeting, if you're going towards moon or Mars or other in deep space, then you can do TLI maneuver, translunar injection, or B plane targeting. So these are different types of maneuvers that you can do. So I would encourage to read through the maneuvers, different types of maneuvers. There's this book, Curtis, Orbital Dynamics by Curtis. I'll just type it here. And there are many other. Valado is also another one. Uh, so I would encourage to read that. I'm not sure. So I'm not a signals guy. So I don't deal with the communication part. So this is uh, so this concept is not about. It has an application to remove that to remove that requirement of ground communication. But here nowhere I used or I needed the knowledge about what kind of signals or transmission frequency is needed. And so I would encourage to read about that, but I'm not aware. I'm not familiar with that because I did not use it for this project. For interplanetary missions, if you want to know about what kind of uh, ground control or ground tracking, it is mostly deep space network. Read about deep space network, and so yeah, that is what I would say. But I'm not sure if I understood the question correctly, but that is yeah. Yes, there are many concepts, many projects that are being proposed for using AI. The only problem here is when you have a spacecraft uh, when you have a space mission, you want to make sure that the concept will work. You like not 100%, 110%. So if you implement AI on board, then the problem with AI sometimes is it is still learning. It is still there are different types. I'm not familiar with AI thoroughly, but there are different types of techniques which AI use. And as far as I know, those techniques are still under development, and they use neural networks, etc., which do not uh, which currently have not reached that kind of accuracy, I would say, that is needed to make sure that the system will perform when needed.
Okay.
So another thing is AI needs a lot of computational resources.
Mm.
So I'm not sure if you have heard, when there was Apollo mission, the computers on board were much less powerful than the mobile phone in our hand today.
Yes.
And it has not improved drastically.
Mm.
Even now, the computers that they use on board International Space Station are, if not 20, at least 10 years behind in technology.
Okay.
So there are computational limitations there. So you cannot use a technique which will take more computational resource, and because you have to segment it for all the purposes, not just for navigation but also communication. For you need computer for all of those as well. So yeah.
Okay. Okay. So, what do you suggest for the young aerospace engineers, those who are coming in the future? Which particular area, research area, you can suggest to them?
Oh, all the research areas are very much in demand.
Mm.
The only thing is, in some areas, you will need to higher degree, higher educational qualification. In some, you can just enter the industry with bachelor's.
Mm.
I can see there was some question about aeronautical engineering. Aeronautical engineering is not as such ITAR restricted. There are
Mm.
much more liberations there. But aerospace, specifically spacecraft guidance and navigation or propulsion, are much more restricted.
Mm.
But if you are interested in there, it is only going to grow. So I would just suggest that expand your skill set, learn much more programming languages, learn
To grow.
other
So,
tools and all, and it will only help. Yeah.
okay. Okay, sir. I think there is no
Excuse
more
me.
questions from our audience also. So it is a great thing. Like I think almost it will be one in the midnight for you, right? So it is a great thing you have spent this much time with us, and surely, as we have discussed earlier also, right? If any student he is interested with space dynamics and controls, surely I will ask them to contact you, and we need your support throughout this career wise as well as we are especially going for MATLAB interdisciplinary some subjects to include in our syllabus and scheme. So, which type of subject you can suggest to us? Because you have done your PhD in Utah State University. So, especially like if you see in India, still now we are having a aerospace engineer as a degree. Only few institution is providing a propulsion engineer or avionics engineer, right? So, whether you think that particularly if we are having a in-depth specialization as a degree, whether it will work or not. So you are in mute. You are in mute. Yes.
Yes, sorry.
Okay.
Yes. I think it will definitely work. Interdisciplinary will definitely help expand skill set. Um, when I was doing this project. I came across a friend who was using a genetic algorithm for his project, for his research. So there are these different genetic algorithms are also available on MATLAB. MATLAB is very powerful. There are so many tools. I still don't know all the tools completely. Excuse me. I would say interdisciplinary will definitely help. There are a lot of because my field includes a lot of simulations. I try to learn more about programming and getting to run simulations faster, analyze better mathematical models behind that. But each area or subfield of aerospace, there are different aspects. So you can definitely plan accordingly, but it will definitely help if you try to learn more skills and try to include more interdisciplinary research.
Okay, another one question. Which programming languages would you suggest?
I would suggest C++ and Python. Those are really much in demand. So yeah, but there are so many.
Okay. Okay, sir. Thank you for your sharing your time, and we can end the session over here. Thank you very much.
My pleasure. Thank you.
Thank you.
Have a good day.
Yes.